Hey everyone, welcome to another session of Backend Study Group with Women Who Code San Francisco. Just a few logistical things to begin with. We'll be recording tonight's session, so if you want to turn off your video or change your name, that is totally fine. Feel free to do that. We will have Q&A at the end of the presentation, but we will also monitor the chat, so feel free to ask your questions in the chat as well. That is perfectly fine. We feel free to take notes as well. There's a raise hand feature at the end. If you want, you can also do that and ask your question. By attending this session, you agree to comply with the Women Code's Code of Conduct. Next session, slide.
Yeah.
Welcome to Women Who Code. Our mission is to empower women to excel in technology careers, and our vision is an industry where women can thrive and excel at different levels. Backend Study Group, we started this couple years ago, where we teach backend engineering concepts regularly, pretty much at least one session every month. And today's session is about data pipelines. So what is data pipelines, how to design them, the tech stack, and some examples. I'm your host for the evening. I'm a senior software engineer at Unity here in San Francisco, and I'm also a director at Women Who Code SF. And I'll hand it over to Harini.
Thanks, Prachi. Hey, everyone. Thank you for joining us tonight. My name is Harini Rajendran. I work as a senior software engineer in a company called Confluent that's based out of the Bay Area. But I'm joining in from Chicago today. So that's where I live. I've been volunteering with Women Who Code since the beginning of the pandemic, and I'm one of the leads of the Women Who Code San Francisco chapter. It's been about 7 or 8 years since I started working after my master's, and my area of specialization is like building and working with big data pipelines. So the examples of the data pipelines that I'm gonna talk at the end of the session are actually the projects that I have been I was working on my previous workplace, and another example is something that I'm working on currently in my current role. So those are like real life examples that are being used in companies. So we can dive in. I'm not an expert by any means, so if you have any questions and if I don't know the answer to them, I'll definitely do some research and get back to you on our Slack channel. And if you're not on Slack, Prachi will share the instructions on how to join our Slack space. So having said that, let's jump into the session. So first, I would like to start with what is the meaning of data pipelines? Like, what are data pipelines, right? So essentially, a pipeline is nothing but a series of microservices or applications, which actually transforms the raw data that are collected from various data sources to an understandable format. And finally, the data that's transformed to an understandable format eventually gets stored in some data store from where it can be used for analysis and modeling by different stakeholders. So what do I mean by that? Let's take an example. So let's say you are a company, you have a mobile app, you have a website, and you have multiple customer facing microservices that are running. And you collect some information, some raw data about your users on these different platforms, let's say. And you are interested in doing some analytics on top of the data. So what essentially data pipeline how it can be used here is, you instrument your mobile app, your website, your microservices, all of these different clients. So whatever is here on this side, we call them clients. You instrument these clients to emit raw data. So from all these different sources, and then you pass them through your data pipeline, which would do all the transformations, cleaning, whatnot. And then finally, it would store it in some data store at the end. And then once it's available in some data store in some queryable format, then all these different stakeholders in your company can tap into the data and use it however way they want it. Like, for example, the executives might be interested in some high level business metrics. The data scientists might actually be interested in some, user related data, like historical data, where they would want to run some analysis on the data. The customers might be interested in just their own data that they are publishing. So different stakeholders might be interested in different section of your data at different granularity, at different frequency and all of that. But essentially, the pipeline is what does all the transformation and finally gives stores the data in a consumable format for all these different kinds of stakeholders. So basically, this is data pipeline, and that's the most common use cases on why we build data pipelines. If you have any questions anytime, feel free to post it in the chat. If I miss it, Prachi will bubble it up and I can answer it, or you can ask them at the end as well. So before jumping into the types of data pipelines, I wanted to spend some time to actually talk through what are the different steps in designing these data pipelines. So these are the various steps. Let's go through them in detail one after the other. So first step in any, not just building data pipelines in any application or microservice development, any software, the first step is usually the requirements gathering. So what are the things that are involved as a part of requirements gathering? Like, you go and talk to the stakeholders, like in this case, could be the analysts, it could be the data scientist, or it could be the executives, and understand the problem and see what data they are interested in, what is the scope of the project, what is the timeline, by when does it have to get delivered, and all of that. What is the SLA? So SLA is service level agreements. Do they want 99.99% availability of your system, or is 95% enough? How much downtime is acceptable in your system, and all of that. How frequently do they need the data, and at what granularity? Do they need hourly data? Do they need daily data? Do they need it at the end of every day, or do they need it at the end of every hour? So you can ask all of those questions. And what's the preferred data format? Do they prefer it in JSON or plain text or Parquet? There are various numerous data formats. So what is it that what data format do they prefer? And also what are the data fields or columns that they are interested in the output that they need? So this phase is very crucial, because unless you have a clear understanding of the requirements from your stakeholders, then you might be developing something that doesn't solve their problem, and it's just a waste of developers' time. So a few minutes of a discussion can save multiple days of development time. So it's always important to do a diligent work when we are collecting requirements. And then the next step is architecture, coming up with a high level architecture. So what are the different pieces in your big data pipeline? How would all the piece fit together? So for each piece, let's say we want a data store, there could be hundreds of different options for data stores. So what are the pros and cons of various options? Which one do you pick? And also how it fits into the existing infra. For example, let's say we have 3 different options for a data store, but then you're already using one of them extensively in your company. So then if you have the existing infra and everything set up for one particular data source, then that data source definitely has an upper hand over the other 2 options. So you might decide to go with that. So yeah, just thinking through all of that and putting together the high level design is the second step in designing big data, in designing any data pipelines. So now you have an idea of how your data pipeline would look like. But then the next step is the orchestration. Okay, so you have the data pipeline. Now, how will the data pipeline be run? Who manages it? Does it run on a schedule? Is there an option to manually trigger the runs? So that those things are usually fall under the orchestration bucket. Like there are tools like cron jobs, which are like primitive scheduling tools where you can go and schedule some scripts at a fixed cadence, or there are like advanced softwares like Apache Airflow where you can schedule jobs, like complicated workflows and stuff using Apache Airflow. So uh, I've personally, like we have personally used Apache Airflow in our company to schedule some bad jobs. So like there are like numerous options for these orchestration tools that's available in the industry. So which one fits your need? So picking all of that, and um, also starting to think about, monitoring and alerting and logging and debugging. So those are some of the things that has to be taken care of as a part of building the data pipelines. So double clicking into logging and monitoring. Logging and monitoring is actually very important, and it's uh, often ignored. Like it's easy to ignore that, and then just like we'll end up coding the whole thing, deploying the whole thing, and then suddenly one day your application would crash, or your application like doesn't boot up, or whatever, some serious problem happens, and then you are running blind. There are not enough logs, there are not enough metrics to monitor what's happening in the system, why it is crashing. Is there like an out of memory error? Is your system like super CPU intensive? When was the last run? When did it pass? Like if it failed, why did it fail? So thinking about all of this right before you start coding your application, and then like considering all of those in your detailed design, or when you're actually coding your application, is very important. So start thinking about logging and monitoring right from the beginning, even before you write a single line of code. This is not only relevant to data pipelines, this is relevant to like if you are developing any sort of microservices or any application, these steps are applicable to them as well. Similarly, testing, start thinking about testing before you write any code. Make sure when you are writing code, everything should be unit testable. If there are multiple technologies that are available, but then if one of them makes testing more easier than the other, then probably like that could be one reason to go with that. And also, like when you are putting together all these different pieces in the big data pipeline, also just think about how to test each and every piece individually, and also how to test the whole data pipeline end to end. So usually the way how we have done it in our projects is, for each piece individually, we usually have like unit tests. But for the whole end-to-end, we would end-to-end testing, what we would do is we simulate like predictable workload as the input, where we would know what the exact output would be, and then we would just send it through the pipeline and verify that, okay, the expected output is produced at the end of the pipeline. So we call it probe testing, because you pass a probe where you know what the result is, and then you just verify it. So that's one way of testing the whole end-to-end pipeline. So this is also something that's generic. It's not like something that's specific to big data pipelines, but the next step, which is data modeling, is something that's specific to data pipelines. So this is very important, because you should have a clear understanding of the data that you are going to be working with in your data pipeline. So what are the data types? What is the schema? What are the fields that are present inside the various data, like the data that you collect from various sources? And when you transform the data within your data pipeline, how does the schema evolve? What is the format of the data when it finally lands in the sink, which is like the data store? If you are collecting data from different entities, let's say users, purchase orders, or whatever, right? Like what is the relationship between all these different data entities? How do they connect with each other? how much volume of data would be generated and what is the data velocity? Would your system be generating like 1 million events per second or like 100K events per second? What is the velocity at which data would get generated? And how would you store the data? Like how would you partition and store the data into different tables or different indices based on the data store that you are finally going to use? So thinking about all of this and having a clear understanding of the data model and how we are going to store it at the end, and understanding the volume and the velocity of data generation are all very important, because that determines, okay, when you finally go to deployment, when you hit a point where you're ready to deploy your data pipeline, then you would know, okay, how many instances of it to run, how big of a machine should you use, and all of that would be clear if you have a better understanding of these things. So now you know, okay, what does the source data look like? What does the sync data look like? You have an understanding of all of that. So then the next would be like sketching out the whole data flow. So when I say the whole data flow, you can think of it like a detailed design of all the components. So let's say you have like 4 components in your data pipeline. How would the input data look like for each component, and what would be the output that particular component is generating? What sort of transformation that particular component is doing? So when you sort of walk through this or think through this through your entire pipeline, it also helps you to identify gaps or holes in your pipeline. You might have missed some things, and it's an opportunity to uncover those even before you start writing code, because like after you write everything, then fixing bug would definitely take a lot more time than fixing it right at the design phase. You might also think, you like while you're doing this exercise, you might also realize that, okay, there's a better way of doing certain things. So you can use that as an opportunity to take a step back and, you know, rethink and do things differently than your initial plan. So just coming up with like a detailed design of the data flow through the various different components would also um, help build a strong data pipeline with, you know, less gaps and bugs. So once you're done with all of these steps, that's when we really get into the implementation part. So finally, we get to the exciting part where you write code. Make sure that you write good comments on your code, follow like proper coding standards and best practices, and make sure you're writing like easily maintainable and extensible code that is also easy to read. Don't write monolithic code. Like follow proper, you know, object oriented modeling, if that makes sense, and proper abstraction, so that it's easy to read and understand, and also it's easily maintainable. And if more use cases have to be added in the future, it's easily extensible as well. So those are some of the things to keep in mind when you're actually like implementing the various components of your big data pipeline. And once coding is done and everything has been deployed, the job doesn't end there. Frequently, we do a poor job in documentation as software engineers. So I like, even like, I'm very mindful of that, and we make sure we like properly documented, because in software industry, as you know, like people keep switching companies. You might start working on a project which was written by someone else. So having proper documentation actually really helps, because I mean, if you write code today, after 2 months, even you won't remember certain things from the code. So having strong documentation is really important for multiple reasons. Some of the things that you could cover in the documentation could be like, what is the tech stack? What is the reasoning behind choosing those tech stack? How to test it, how to deploy or install or build your application? What is the data model? What are the different sources and things like that. So whatever you think um, is important, like important information to, you know, document somewhere. It's like a one-time effort to written documented, but it would come very handy as the project grows in complexity and as more and more people starts working on the project. So the documentation is also a really important step while building not just data pipelines, but in building any software. Any questions so far? All right, let me go forward. So there are you can broadly categorize data pipelines into two different types: batch processing and stream processing. So first we can see talk about the batch processing data pipelines. So this is when data pipelines started becoming famous. It started with batch processing pipeline. So these are the traditional analytical tools where data is usually collected over a period, let's say a day or a few hours. So you keep collecting historical data over a period, and then this batch of data is loaded into a software, and the jobs are scheduled. These jobs usually run for a few minutes to a few hours, sometimes even days, depending on the volume of data and how frequently we are running the job, etc. Since it's batch of data, usually the volume of data that is handled by these jobs are really high. As you can see, since these jobs could take from a few minutes anywhere to hours or days, this kind of batch processing is can only be used for non-urgent tasks or non-urgent reporting. Let's say you need some monthly accounting data, or at the end of the day you need some daily summaries. So for things like that, where you need to crunch high volume of data, but you don't worry about getting the result back in, let's say, milliseconds or seconds, and then those are perfect use cases for the batch processing. So we usually also call them as ETL pipelines. So ETL stands for extract, transform, and load, where each phase represents a certain aspect of the data pipeline. The extract phase is the phase where you get data from all these different data sources. You extract data from all these different data sources that we saw earlier. And then the transform stage is when all this data that's collected from these different data sources are loaded into some temporary staging area, like a software where it does all the transformation that's needed. And then finally, the transformed data is loaded into the final sync, which is usually some sort of a data store or some sort of a blob store from where it can be queried. So these are the three steps: extract, transform, and load. So this is how batch processing usually works. So to show that pictorially, it's the same thing. So different types of sources are generating data, and the batch processing software loads them and then transform the data based on the business logic that we are interested in. And then it's also stored in some data source, and then finally the stakeholders business intelligence people or representatives or whoever, they can query this batch processing software or the data store to get the data or trigger a job and then get the result that they are interested in. So this is how a high level batch processing pipeline looks like. We'll see specific example towards the end, but this is how at a high level a batch processing pipeline would look like. And the other type of data pipeline, it's called stream processing. So in batch processing, we saw that data is collected over a period historically, it could be daily or monthly or whatnot, and then loaded into some staging area and then transformed, right? But stream processing is real-time analytics. As and when data is constantly flowing in, the application, the real-time data pipeline is constantly crunching it in real time, and then it's constantly deriving insights from the data within milliseconds or even seconds. So that's the main difference between the batch processing and the stream processing. So here, the data crunching and the insights generation, everything happens in real time. And similarly, like whenever any sort of query is submitted to the stream processing application, there also you would usually get the response in milliseconds to seconds. But because of this aggressive processing of the real-time events, the real-time stream processing pipelines are not as reliable as batch processing pipelines, because there are more chances of data getting lost, or sometimes the volume of data that gets ingested might be too high that your stream processing application is still catching up and it has not consumed all of the data. So the insights that you are getting might be incomplete. So it's not as reliable as batch processing, but nowadays with all the big data, with all the humongous amount of data that we generate, like we do see a lot of these streaming data pipelines in the industry. Some of the use cases for stream processing would include like real-time operations. For example, let's say in my company, we run a lot of service. We run a lot of products as service in the cloud. Like we run Kafka as a service in the cloud. So we continuously monitor our Kafka fleet in real time, and then based on what insights we get, we take appropriate actions. For example, if we see that one of our cluster is running out of space, we monitor it, and then we immediately trigger like a cluster expansion. And this is not something that could wait till the end of the day. This is something that should be decided within minutes so that the cluster can be expanded and our customer has good experience using our software. Another example could be like real-time trading. Like all the trading softwares usually like would be using some form of stream processing pipeline in the backend, because they are like even like milliseconds or seconds play a huge role. So they are also used in such high frequency trading. One other huge example is autonomous vehicles operation. So in the autonomous vehicles actually generate like huge amount of data, and all the data that is generated are constantly like being analyzed in real time so that appropriate actions can be taken. Let's say the car is going over speed, it is immediately processed, and then the autonomous vehicle would slow it down or whatever, right? So that is another example where these real-time stream processing data pipelines can be used. And also like real-time inventory updates. Whenever you have any inventory which needs to be updated in real time, I mean, that's one other use case where you can use these real-time stream processing applications. Yeah, so those are some of the use cases. So the way how the stream processing pipelines look is like similar to the earlier one. Like there are all these different data sources, like these edge devices, IoT devices, sensors, websites, user applications, or mobile devices that are constantly generating events in real time at high volume. And all those events are passed through the stream processing application, your data pipeline, and then the stream processing engine continuously like generates insights within like maybe like few hundred milliseconds to few seconds, and then like you can do some sort of real-time analytics on the data that's being generated by your stream processing application or the pipeline. So this is how like a general stream processing pipeline would look like at a high level. So now just iterating over this, like so we saw both batch processing and stream processing pipelines, right? So what are the different aspects of any data pipeline, be it batch or stream processing, right? So there are like 5 different steps here. Just to summarize, so the first one is source app instrumentation. So again, to reiterate, you instrument your websites, applications, microservices, or any of the clients to produce the data that you want to transform and like derive some insights out of. So that's the first step. If there is no data, then there is no point in building any pipeline. So like instrumenting your applications to generate the data that's of interest to you is the first step. And then whatever data is instrumented, then gathering all the data to a centralized place. So that part is usually called as ingestion. In most big data pipelines, usually like storage like S3 or Kafka is usually the entry point in the big data pipeline. So that's where all the data ingestion happens, and all the data from all these various data sources gets ingested first. And then the rest of the pipeline would consume from that Kafka topic or S3 bucket and then process it at its own pace. And this is the general model, because usually events get generated at a high rate. For example, in our current project, we get events at the rate of 1 million events per second, or even a little more than that. But then our microservices aren't as fast to actually handle 1 million events per second. So the way how it works is we have like a very thin thin layer of application and microservice at the beginning of the data pipeline. All it does is it receives these events and then just writes it into a Kafka topic or just writes it into an S3. It doesn't do any business logic. It just gets the event and writes it. So that first thin microservice does nothing. Since it's so lightweight, it can handle that 1 million events. And it would put it in a central storage. And then our actual microservices, which does all of the business, which has all of the business logic, which does all the required transformations, they slowly read this data from Kafka or S3 at their own pace, and they would process it and then send it to another another application, in the data pipeline. And finally, after all the different transformations, data would get stored. So in the ingestion, the first piece is usually like one of these softwares like Kafka or S3, where data is collected from all the data sources and it's stored in a centralized place. And then, as I mentioned, the next step is processing. All the data that is gathered in Kafka or S3 are now cleaned, transformed, and processed by the different components of your big data pipeline. And then that's where, like, if it's a batch processing application, you would use softwares that fits that use cases, or if it's a stream processing application, you would use softwares like Spark, etc., where you do like real-time processing. So once all of this processing is done, be it batch or stream, they finally get stored in some data store. Usually, like in this day of big data, big data, we usually store the data in some distributed storage systems. Usually it might be S3 or any of the NoSQL databases, like, Elasticsearch, PostgreSQL, or, MongoDB, Druid, and all of those. So once this whole transformation and everything is done and data is stored, it doesn't stop there. And data is of no use unless someone can access it and query it and use it properly, right? So that's where the final aspect comes into picture, which is access. Again, not everyone should be able to access everything. Like, it depends on how sensitive your data is. Let's say you're working with some health related data or some finance related data, then you should make sure that only certain teams or certain people in your company has access to the data, whereas there could be some less critical data which can be opened up to the whole organization. So thinking about data access is also very important. And also data organization, like how do you want to store your data in such a way that it can be retrieved it can be retrieved very fast, like maybe in few milliseconds or under a few seconds. based on the needs of your system. So here thinking about permissions and also thinking about strategy on how you would want to store the data for faster access. It's also an important aspect of building big data pipelines. Any questions so far?
None.
Okay. All right, I'll go ahead. So now I've given like some examples of the common technologies that are used in the industry to build big data pipelines. So if you are building like a stream processing, a real-time stream processing big data pipeline, you would see like at least one of these being used in the pipeline, like Apache Kafka, Amazon Kinesis, Apache Spark and Flink. So these are like real-time. Apache Kafka and Kinesis are like real-time message queues where you can publish messages to it and then read messages from it at high volume. And Apache Spark and Apache Flink are real-time processing software. So it can read data from anywhere, does all the transformation, cleaning or whatever business logic you want, and then they would emit the output in real time as and when it processes the data. So these are some of the most famous stream processing applications that are used while building real-time big data pipelines. And with respect to batch processing, Hadoop MapReduce is one of the famous ones. There you can load like huge volume of data, maybe at the end of the day or even at the end of the month, and run your batch jobs in a staging area, and then you could finally store the output of the jobs wherever you are interested in. So Hadoop MapReduce is one very common software that's used for batch processing. We can also use Apache Spark there. So Spark does something called as micro batching. So it doesn't like batch data at a huge volume like Hadoop MapReduce, but then it also doesn't process data one event at a time. It micro batches, it processes the events in like very, very small batches. So you could actually like consider Apache Spark both as a batch processing software or a stream processing software. It depends on how you look at it. And then in this era of high volume of data, after doing all of this cleanup, transformation and everything, finally you have to store the data somewhere so that the different stakeholders can access it. So there are like a few different types of databases and data stores in which the data is usually stored, like SQL, Postgres are some of the examples of relational database. I see someone has a question, so I'll just finish the slide and then you can ask your question. And then some of the common examples of NoSQL databases are, MongoDB, Elasticsearch, Cassandra, etc. Each one of them is has like can be used for different use cases. For example, if you have like if your output is so text heavy and you want to do some searching and querying on heavy text data, then like Elasticsearch is very useful. If you have a time series database and you want to run some sort of real-time analytics in your time series database, then Apache Druid is a very good example. If you have a lot of documents like blobs of data that are like JSON data and stuff, on which you want to run some sort of an analytics, then MongoDB could be a good fit there. Or let's say you just have a bunch of key values that you want to store and query, then Cassandra could be a good example there. So I mean, good fit there. So based on your use case, you can pick like a relational database or one of these NoSQL databases, or if any of the blob stores like S3, HDFS, Azure Blob satisfies your needs, you can just dump your process data in those data stores as well. please go ahead with your question. You can unmute and ask the question.
Yeah, I do have a question about the batch processing. Just to clarify, is the batch processing converting raw data into usable data? Is that correct?
That's right. Yeah, both batch processing and stream processing essentially does that. It's just how frequently it's done. Batch processing usually like is not run on real time. We collect like a huge volume of data, let's say a day's worth of data or even like a month's worth of data, and then load all of the raw data somewhere. The batch processing software would process it and crunch it and give you the result. Whereas the stream processing pipeline also processes the raw data, but it processes it in real time as and when data is generated, rather than waiting for a certain period and then processing them. So that's the difference between the two.
Okay, and then like for the data store, are those all cloud-based?
It depends. Like all of these, like if you see Amazon, like Amazon S3, Azure, those two are like cloud-based because they are offered by Amazon and Azure. But then if you take MongoDB, Elasticsearch, Cassandra, all of these are actually like open source databases. So, and there are cloud offerings as well. So if you decide to run them on-prem, like, and manage it by yourself, you can install in your own data centers and manage them. Or you can use one of the cloud offerings and just, pay for the service and use it. So if you have both the options, you can manage it yourself or you can use the cloud offering, because all these are just open source databases that anyone can download and install.
Okay, yeah, that's all the questions that I have. Thank you.
All right. Yeah, now I would like to just talk through a couple of data pipeline examples that I've worked on in the past. So like I put two examples here. If you see both the examples, like you can immediately recognize like a common pattern there. So the way how any data pipeline usually starts is like there are like data sources, as we mentioned. It could be website, application, mobile app, or whatever, right? Which actually generates events continuously. And then the first entry point is usually like a load balancer, because like the amount of data that gets generated by all your clients is so huge that one service cannot handle them. So usually all of this data would hit a load balancer, and the load balancer just blindly, sprays the data across multiple instances of the microservice that's running in the front line. And this is the light microservice that I spoke about, where all it does is just receive the data from the load balancer and just dump it into Kafka. Pretty much that's it. It doesn't do anything more. And then once data is there in Kafka, now in our previous company, we had two different data pipelines that were working on top of the data that's inside Kafka. So first, I'd like to talk about the real-time pipeline. So in the real-time pipeline, we had like a bunch of microservices that actually like read data from Kafka. It did some data cleaning, it ran some data transformations and stuff. And then finally, like the data that is processed was stored in Elasticsearch. That was the database that we were using. And then there we had like a microservice that was sitting on top of Elasticsearch. So this microservice that you see here actually exposes like public REST APIs. So usually the way how it works is we don't let UI, or we don't let customers or anyone talk to the database directly, because let's say today we might be using Elasticsearch, tomorrow we might decide to switch from Elasticsearch and use a different database. So it's never a good idea to let your final users talk to the database directly. So that's where we always put like a microservice in between, which exposes well-defined public REST APIs, so that the REST APIs would always stay constant. It wouldn't change. But the microservice, if you switch Elasticsearch to a different data source, the implementation in the microservice is all we have to do, because then our microservice would talk to the new database instead of Elasticsearch, gets the results, and it returns it to the client. Yeah, so in this use case, we were using the REST APIs to, query and plot charts in our dashboard. And we also had APIs that were exposed to customers. So if customers are interested in some of the data that they publish, they usually like make these API calls, which would land in these microservices, which in turn would go talk to Elasticsearch, gets the response and sends them back back to the client. Yeah, go ahead. There's some question.
So so the microservices are there because you don't want the customer to change the data. Is that correct? Or
No, actually the data, most of this big data pipeline, the data would be immutable, but we don't want customers to interact directly to data source, because let's say the way how you query Elasticsearch might be completely different from the way how you query, let's say, Postgres. Today we are using Elasticsearch, and let's say we see that Elasticsearch is not a good fit and we decide to switch it to Postgres, then all the customers and API users should change the way how they query, right? So that's where we maintain a microservice in between, which exposes like standard API. So all the end customers would only make those standard API calls, and the microservice in turn converts those API calls into, this software specific queries the database, and then gets the response back, again constructs it into like a well-defined format and sends it back to the user. So this layer would always stay constant even if this changes, because if this changes, the communication between the microservice and the database is the only part that has to be changed, whereas customers can just continue querying the microservice as is without any change from their end. Does that make sense?
so it's like a standard process. Is that why microservices are used?
Yeah, that is to make sure, customers have like a unified experience irrespective of whatever we change in our pipeline in the backend.
Okay, got it.
Yeah. All right. So this is the real-time pipeline that we had. So the microservices were constantly ingesting data from Kafka, and it was getting stored in Elasticsearch, and we were using them to plot real-time graphs. And we also had a batch ingestion pipeline. So we were using like Apache Spark and Hadoop file system as like Hadoop as the storage in our batch ingestion pipeline. So we had one set of Spark application that was reading data from Kafka. It did some preliminary transformation and stored it in Hadoop. And then at the end of every day, so this was happening in real time, and then it would get stored in Hadoop. And then at the end of every day at night, at night, there were another daily jobs, Spark jobs that would get triggered, and they would read from this intermediate. Hadoop does all the job process, like all the processing of the data, and it would store it in another Hadoop folder. And once the data is there in the final Hadoop folder, then we had another set of Spark jobs, which, our stakeholders wrote, that were running also at a daily cadence. So those jobs would query this transformed data and then produce the appropriate, like the necessary output that those stakeholders are interested in. So this is the ingestion pipeline where we do all transformations and finally store it in Hadoop. Once the data is stored in Hadoop, then our customers, our stakeholders also ran jobs, at a daily cadence using our job infra. We had a job infra. So there the stakeholders can come and schedule their job, saying, hey, run this job at 12 noon every day and give me the output. So the job infra would schedule that particular job. It would crunch whatever data is needed from this Hadoop file system, and then it would give the result back to the stakeholder. And so these were like daily jobs that we were running in our batch ingestion pipeline. So this is an example of a data pipeline where for the same set of data that's there in Kafka, we had one real-time pipeline and we also had a batch pipeline, and those two were solving like different use cases. This is an example of the data pipeline that I'm working currently. So this particular project only has a real-time ingestion pipeline, and there is no like batch ingestion pipeline that's there. And you can see like it's the similarity with the previous pipeline. Similarly, like there are different data sources that are generating data which lands in a load balancer, and there is a lightweight microservice at the beginning which just fetches data from the load balancer and loads it into Kafka. The only real difference is the kind of data source that we use here. So in my current project, we use Apache Druid, which is like a time series real-time analytics data store. So that actually has direct integration with Kafka. We do not really need any microservice in between to read from Kafka and write it into Druid. Druid itself can directly read from Kafka. So we read from Kafka. Druid has plugins which we can implement to do all the transformations that we are interested in. So we do that, and data finally gets stored in Druid. And similar to the previous pipeline, we have a microservice layer on top of Druid, on top of which customers usually run REST API queries. And same way we use it to plot, we use it to plot our dashboards, our UI, and our customers also run REST APIs against this microservice. And all this microservice does is it translates the customer query into Druid query, gets the response from Druid query, puts together the REST API response and sends it back to the client who made that query. So sort of similar, like most big data pipelines you see like would follow like this sort of a model, just that the different components could be different. Like instead of Kafka, it could be like Kinesis. Instead of Druid, it could be Elasticsearch or Cassandra or whatever. But yeah, so it's nothing but a collection of microservices and these softwares put together that does the job that you want, which you can eventually query at the end. Yeah, pretty much that's all I had for the introduction of data pipelines. So these are all the references that I used. We have some amazing sessions coming ahead. We have like a Ruby on Rails session next month, domain-driven design and web development 101. We would also be scheduling more sessions for July and August. So keep an eye on the meetup events and try to attend those. Yeah, in our chat, Prachi would be sharing details on how to join our Slack space, how to get access to our GitHub repository, how to access our YouTube video recordings, etc. So if you have any questions from our today's session or anything with respect to backend, feel free to post it in our Slack channel. Yeah, if you have any questions, I'm happy to answer.
I see one question from Larry about Ruby. Ruby, a lot of startups actually use Ruby on Rails as a tech stack because it's very easy to development time, just starting an application, all of that is very easy. It's not, the concepts are not as complicated as let's say Java or Scala. So Ruby is definitely a skill or a tech stack used in many startups still today. So definitely it's in demand. It's not like as fancy as, I don't know, people talk about Python or other tech stacks all the time, but a lot of startups actually use this. I'll actually stop the recording, Harini.
Oh, yeah.
Yeah.